Welcome. We have been looking at the Neumann principle, which says that the point group symmetry of a given material and the symmetry of any given property in that material, that the symmetry of the property should include the point group symmetry. So, it can be bigger than that or it can be larger than that, but it should at least include the point group symmetry of the crystal. So, in this context we wanted to understand what is a symmetry element and what is the point group, etc. So, let us start with the notion of a group. So, let us consider a set which consists of 4 elements, namely plus 1, minus 1, plus I, the imaginary number or complex number, and minus I. Right. So, this is a set. So, let me write it down: 1, minus 1, plus I, and minus I. Now, we can form a multiplication table consisting of these 4 numbers, and this is a multiplication operation, and then we write the same 4 numbers and we fill this table. So, 1 times 1 is 1, this is minus 1, this is I, this is minus I, and this is minus 1, this is plus 1, this is minus I, plus I, and then I, minus I squared is minus 1, minus I squared is plus 1, and this is minus I, this is I, then minus I squared is plus 1, and minus I into minus I is plus I squared, which is minus 1. Now, there are certain properties which are satisfied in this kind of multiplication table. First one is known as closure. This entire table, the multiplication table, consists of only 1, minus 1, I and minus I, which means that our set consists of these 4 numbers. Under the multiplication operation, you get the same 4 numbers in different combinations. So, this property is known as closure. Second property is known as associativity. This basically tells that the order in which you multiply is not important. For example, let us take I into minus I into 1, for example, which is equal to I into minus I multiplying 1. Why is this? So, this is I, this will be minus I, and I into minus I will give you minus I squared, that is minus 1, I squared is minus 1, minus I squared is actually plus 1. So, this will give you 1, and here you again have minus of I squared equal to 1, and that is 1. So, you get, so the order in which we multiply, whether you multiply minus I with 1 first and then multiply to I, or you multiply minus I with I first and then multiply that with 1, the order does not matter. So, this you can check for many different combinations and you will find that they always give you the same result. This is known as associativity. Then there is the notion of a unit element. So, what we mean by that is that for every element there is one element which if you multiply you get the same element. That is, for every element, let us say A in a group, the unit element is an element which has the property that you multiply it, left multiply or right multiply, you get the same element, right. So, in the case of 1, for example, if you multiply it with 1, you get 1, and if you want to get minus 1, and you can multiply it with 1 and you will get minus 1, I, for example, with 1 will give you I, minus I with 1 will give you minus I, and it is the same in the other way also. So, minus I with 1 will also give you minus I with 1 will give you I, and minus 1 with 1 will give you minus 1, 1 with 1 will give you 1. So, there exists an element which is known as the unit element, which if you multiply, left multiply or right multiply, it gives you the same element. So, this is known as unit, and then there is an element which is known as the inverse. So, the inverse for any element A has the property that A inverse or A inverse A will give me I, the unit element, because in this case the unit element is 1. For 1, for example, multiplication with 1 gives 1, for minus 1 multiplication with minus 1 gives 1, for I multiplication with minus I gives 1, and for minus I the multiplication with I gives 1. So, the unit element is recovered by these elements. So, those are known as the inverse elements. So, we define a group as follows: if you have a set of elements and if you can define an operation on these set of elements, in this case it is called multiplication, sometimes it is called group multiplication or group addition, and under the action of this operation, if the given elements satisfy all these 4 properties, namely that the multiplication table such that only those elements appear. So, this is known as closure. So, the operation between different elements results in elements of the same set being reproduced, and the operation is associative. It does not matter in which order you do this, and there is a unit element such that for every element left multiply or right multiply this unit element, you get the same element back, and for every element there is an inverse element, left multiply or right multiply this inverse with the element, you will get the unit element. So, if you have a set with a given operation which obeys all these properties, then that is known as a group. Okay, this set now, but to define the group we also have to identify what is the operation. In this case, this is the multiplication operation. Now, this is one of the groups of this type. You can also think of another group. For example, I can consider the angular addition modulo 360. So, let us consider another set which consists of 4 elements: 0, pi by 2, pi and 3 pi by 2, right. So, if I have addition, but addition this is modulo 2 pi, right. So, 0, pi by 2, pi and 3 pi by 2, and here it is 0, pi by 2, pi and 3 pi by 2. So, 0 plus 0 will give 0, 0 plus pi by 2 will give me pi by 2, 0 plus pi give me pi, and this is 3 pi by 2. Now, pi by 2 will give me pi by 2, then it will give me pi, and it will give me 3 pi by 2, and this will give me 4 pi by 2, which is 2 pi, which is nothing but 0. Now, this will give me pi, and then this will give me 3 pi by 2, and 2 pi is 0, and then pi plus 3 pi by 2, which is 5 pi by 2. So, 4 pi by 2 is 0. So, it will give me a pi by 2, and now this will give me 3 pi by 2, and then this will give me 0, and so 2 pi. So, it will give me pi by 2, and 3 pi by 2, 3 pi by 2, 6 pi by 2. So, that is 3 pi. So, 2 pi goes. So, it will give me a pi. Now, you can say that the set consisting of 0, pi by 2, pi and 3 pi by 2, where the group addition is addition modulo 2 pi, forms a group because it has closure, and for every element, for example, if you add a 0, you get the same element back, and for every element you can find an inverse element, which if you add you will get the same element back, for example. If you add that inverse element to this element, you will get the unit element, which is 0 in this case. Okay. So, this is another multiplication table which has all these properties. So, closure, associativity, unit and inverse is available here also. You can also think of another such multiplication table. Let me consider the complex plane, and let me consider a unit vector of length 1, and if you do a 90-degree rotation, that is going to become I. If you do another 90-degree rotation, that is going to be minus 1, and if you do another 90-degree rotation, that is going to be minus I. Now, they can be represented as for example, e power I 2 pi, that will be 1, e power I 3 pi by 2, and e power I pi and e power I pi by 2, right, pi by 2, pi 3 pi by 2, 2 pi. So, you can also think of, so this is basically r e power I theta form. So, you have a unit vector and 90-degree rotation of that is going to. So, under this operation again you will find that you can put e power I 2 pi and do the multiplication table. There is yet another way of thinking about this. You can think of this as I squared, which is equal to minus 1, I cube, which is equal to minus I power 4, which is equal to 1. Okay. So, now I mean this, so you can represent all the elements like in the first group that we had, which had plus or minus 1 and plus or minus I. So, the elements are all represented in this form. In other words, you have a group elements of which can be represented as a squared, a cube and a power 4, which comes back to unit itself, right. So, now the order of a group right, if it is a finite group, okay, is the number of elements in the group, that is the set over which the given operation is defined. In that set how many elements are there, that is considered as the order of group. Now, this kind of group is order 4. So, it is also called a cyclic group of order 4. Cyclic group because it has this kind of property a squared, a cube, a power 4 equal to 1. So, cyclic group of order n will be, for example, that goes something like a cube etcetera up to a power n, which becomes 1. Okay. Now, in a group, now there are certain things that one can define. The first thing that you can define is what is known as a subgroup. So, let us take the multiplication table that we defined for the 1 minus 1 I minus I, 1 minus 1 I minus I. So, I had 1 minus 1 I minus I, minus 1 1 minus I minus I minus 1 1 minus I 1 minus 1. Now, in this you can define what is known as a subgroup. For example, trivially the entire group itself is a subgroup, but within that, I mean non trivially, there is a proper subgroup which is made up of by these two elements, right, because between 1 and minus 1 again there is closure, there is associativity, there is unit and there is inverse. Okay. And then of course, the entire 1 minus 1 I minus I becomes a trivial subgroup, and this is known as a proper subgroup. So, within a group, a set of elements which form a group are known as subgroup, and there is also this notion of isomorphic, that is, if you have multiplication tables. So, we have seen till now 3 different multiplication tables. So, all 3 tables are identical except for the way in which we labeled the elements. So, they are all said to be isomorphic to each other. So, these are identical multiplication tables except for symbols. Okay. Now, the notion of a symmetric group is that for certain geometric objects there are symmetry operations and those operations form a group. So, what do we mean by that? We will do that in the next part of this lecture. Thank you.